Hello, everybody. Welcome to this week's Green Bank Observatory Community Zoom. Just a few announcements about what's happening at the observatory. We're in the middle of our maintenance period. We've replaced a large section of the concrete in the foundation, and that work all looks very good. We are now replacing some of the grout pockets. So we're shoring up the foundation of the telescope and making sure that the telescope survives another 20 years at least. So that work is all going well. The telescope is being inspected by engineering firm for structural inspection. That is all going well, and we'll get the report in a few weeks. So that's the summer maintenance usual activities here. In September, we're going to replace a few of the wheels, including two of the damaged wheels, two of the wheels that show slight damage. And we will do that on a regular cadence now in the coming years, replacing a few wheels every year as the wheels are manufactured. So all is going well on the upgrade project, and we're on schedule and on budget, so that's very positive news. The proposal deadline for the observatory for the next batch of proposals is 2nd of August. So please send your proposals in, and if you need help, submit a help desk ticket. All right, so with that, I'll hand it over to Jay, who will introduce today's speaker. Thank you.
Thanks very much, Jim. Today's speaker is Spondan Choudhury from the Korea Astronomy and Space Science Institute, and he will be speaking on ammonia observations of infall into subsonic filaments of the B5 core. Let me remind everyone that this presentation is being recorded and will be available for later viewing on our website, and please submit questions through the Q&A button at the bottom of the screen, and we'll deal with those at the end of the presentation. Take it away, Spondan.
Thanks, Jay. Thanks, everyone, for joining, and thank you for the invite for presenting my results here in this webinar. I'm going to share my screen. Okay. Okay. So, as Jay mentioned, I'll be presenting some of my results using ammonia observations to trace infall in subsonic filaments inside a low mass dense core, Barnard 5, in the Perseus region. First, let me introduce the region that I'm looking at. This is a subsonic dense core in the Perseus molecular cloud, which is one of the nearby star-forming regions. The core in single dish observations looks somewhat like this. These are also ammonia observations done previously. This is Pineda et al. 2010. In the ammonia observations, it could be very easily seen that there is a subsonic region inside the turbulent molecular cloud, and at the boundary of the core, there is a very sharp transition from subsonic turbulence to supersonic turbulence in the cloud. This region has also been studied with the VLA. These results from Pineda et al. 2011 shows some further structures inside the core, more specifically two filaments inside the core, and then there is also a known young stellar object, IRS1, in one of those filaments. So these filaments actually present us with a unique opportunity to study subsonic filaments inside a dense core, which are very compact. The filaments are very compact, and they allow us to study the different stages of star formation and in the filamentary structures. These are not the long scale filaments that we usually observe in continuous observations, but these are rather very compact and small scale filaments inside the dense core. This region has also been studying combining the VLA and GBT data by Schmideke et al. 2021. And this revealed further structures inside the filaments, which are shown here. So there are actually a hierarchy of different scale structure in this region, and this presents us with a very unique opportunity to study star formation at different scales using ammonia. Now I'll briefly mention why we are focusing on ammonia for the observation. Ammonia gives us a very unique opportunity and it's a very useful tracer for this purpose because ammonia has a relatively lower critical density, about 10 power 3 per centimeter cube. However, the individual transitions they contain multiple hyperfines as shown here. This is the ammonia 1,1 inversion transition, and as you can see, there are multiple hyperfines of this transition, and individual hyperfines they can be optically thin even at higher column densities. So what it does is it allows us to study different levels of structure inside the molecular cloud, for example, the cloud, the dense cores, and also the filament using the same tracer. By using the same tracer, we can ensure continuity in the physical properties that we are measuring, and thereby we can be sure that we are tracing the transition in continuously in the physical scale as well. There are other benefits of using ammonia as a tracer. Since we have multiple hyperfines closely spaced in the same transition, we can get a very accurate measurement of the velocity and the velocity dispersion. If we are able to detect another ammonia transition, the next inversion transition is the 2,2. So if we detect both of these transitions together, then we can also get a direct measurement of the kinetic temperature without assuming any radiative transfer. Now on to the observations that I'm using. I'm using the combined observations of ammonia using GBT and VLA. The original beam for this data set was 6 arcsecond, but I smoothed it to a slightly larger beam of 8 arcsecond to get a more extended emission and to allow for multiple component fitting, which I'll come to a bit later. The data was fit using the Python package PySpec-Kit, and we used a Bayesian analysis method to get the optimum number of components in each line of sight. This is because we are attempting multiple component fit towards all of the pixels, but since we don't have enough signal to noise to fit multiple components in the outer pixels mainly, we use this Bayesian analysis to determine which number of component is the best fit model. Now the results give us a different number of components towards in different pixels. In this map, I am showing how many components were decided to be the optimum number of fit in each pixel. As you can see in the extended part of the core and the cloud, we are able to fit only one component since the signal to noise, since the sensitivity is not good enough for more than one components there. But in the central parts of the core, mainly the filaments, and then in the filaments, we are able to detect two components. And in the central part of the filaments, sometimes we are able to detect even three. The spectra and the fit, some examples are shown here on the right-hand side on these pixels. So from there, you can see we have this broad component, which is relatively constant in all of the pixels, which represent the cloud component in this case. But we have one or two additional components in some pixels, which are subsonic, which are narrower in line width. And I'll come to the classification of these components just in a minute. But what is important from this is that we are detecting some additional components apart from the component that was already seen with the single disk result and with a single component fit from previous studies. So the first component that we can get from our analysis is relatively similar. It's very close to the results from the previous studies using the single component fit. But this is not very interesting. The interesting part is what we get apart from this component. These are the 4 components that we detect in addition to the single component results. So we have classified these components based on their relative redshift or blue shift from the extended component here. So there are 2 blue shifted component and 2 red shifted component which we detect additionally and which are new results compared to the previous single component results. Now the extended component, if we look at the velocity and the velocity dispersion maps, we can see that this actually show the dense core and the molecular cloud, very similar to what we saw previously with the single component results from the previous works. So for example, in this panel here, I'm showing the velocity dispersion of this component, the extended component, and you see the inside this dotted contour, the velocity dispersion is subsonic, and this is the subsonic dense core that we saw previously in the other results. And then outside the boundary, you see that velocity dispersion, it changes very sharply to the supersonic turbulence region. And then inside, we also have, I'm also showing this filaments in the dense core, and you see the velocity dispersion is very subsonic, very low in these 2 filaments. In the velocity field, we see that the component has a very smooth gradient. There is no sharp gradient across from east to west, but there is a periodic gradient from north to south. And yeah, these results agree well with the previous results of this region using ammonia. Now on to the additional components. So there were 2 components which were slightly redshifted and blue shifted from the extended component, and these seem to be constrained to the filaments mostly. So the redshifted and blue shifted component here, they are detected not in all of the pixels in the filament, but most of the detections are inside the filament. And these appear to be the red and blue shifted component of the same material which is connected to the filaments. For this reason, we conclude that these 2 components are tracing the 2 opposite sides of infalling material in the same line of sight. So when we look towards the filament in its pixel, we see the filamentary material, but we are also, in this case, we are also seeing 2 sides of infall going away from us and then coming towards us. So this schematic shows what we are seeing in this case. So the blue shifted and red shifted component, they are 2 opposite side of the envelope of the filament, which are undergoing infall. And when we look in this line of sight, then we see the red and blue shifted component, but in the extended component, what we see is the middle part, which is continuous with the subsonic core and then the dense the cloud. We can, with a very simple geometry, with like if we consider cylinders to give us a brief idea of the volume that these filaments are encompassing, we can get an infall rate using the infall velocity, which is the average of the difference of these two velocities. So using these very simple calculations, we can get an infall rate of 1.7 into 10⁻⁴ solar mass per year. I should note here that this is an upper limit, since we are not exactly sure of the density of the of these two components, but in this case we are assuming the density of core material here. This infall rate is significant because it gives us a doubling time of 6 or 7 into 10 power 4 years, which is considerably shorter than the average core lifetime of 1,000,000 years. So if we have this infall rate for a long time, then we actually can increase the mass of the filament by a considerable amount during the evolution of the core. Another one of the additional components we observe is this component that I'm showing here in blue. Again, in this case, since the sensitivity is low and we are tracing some material in the core and not towards the filament, we do not have a lot of measurements in this component. But we can see that this component has a velocity that is similar to the velocity of the outer molecular cloud towards the north side. So there, for this reason, we hypothesize that this blue component, additional component, could be tracing some infall of material onto the core from the cloud from this side. So this material is basically a cloud part, which is falling onto the core towards the center. So we can get infall of we can get the infall rate using the difference of velocity from the blue component and the extended component that we see here. Again, we assume a very simple geometry using a cylinder, but in this case, we have even less number of detections, since now we are going into the extended part of the core and we do not have the sensitivity sufficient for the detection. Again, we get the upper limit on the infall rate, and this rate is significant if we consider the core lifetime, because it tells us that we can increase the mass of the core by a significant amount, again, during its evolution. So I'll briefly mention some of the future work that could be done and actually ongoing in this case. One of the follow-up that I'm trying to do is to get like the density of the material that's falling onto the filament as well as to the core. Because with ammonia observations, we cannot really get a estimate on the we cannot really get a strict estimate on the density of the material that's undergoing infall. In our calculations, we assume typical density of the core material and the cloud material for calculation of the infall rates. But to say how much material is actually going to undergoing infall, or how much mass can the filaments or the core increase in its evolutionary lifetime, we need to get a fixed measurement on the density. And for this purpose, I'm actually observing with low density and high density tracers with the TRAO 14-meter telescope in our institute here in Korea. The goal of these observations are to see if the material that's undergoing infall is more like the core material or more like the cloud material. I'm using different tracers. One is the HCN, which usually detects the dense core material, and then also I'm using two isotopologues of carbon monoxide, which usually trace the large-scale molecular cloud. And by comparing the distributions of these different tracers and also with ammonia, I will try to conclude on the nature of the material that's undergoing infall both towards the filament and towards the dense core. I didn't really have time to go through this, but there is there is evidence that the filaments in this core, filaments in this region are supported by magnetic field. This is because we observe both filaments to be very, very highly supercritical in mass, but we do not really see any significant infall rate in the plane of sky. The infall that we observe with the results I presented here, that is in the line of sight. But in the plane of the sky, we do not see any strong infall gradient, and the mass per unit length is highly supercritical, and we actually should be seeing some strong gradient across the plane of sky. But since we do not see this velocity gradient in ammonia, these two filaments need to be supported by something other than gravity, and one of the candidate is magnetic field here. The other candidate is turbulence, but since these two filaments are very subsonic, this is also not a viable candidate. So we targeted these two filaments with JCMT, and we are using polarization observation to determine the strength and distribution of magnetic field. We have some preliminary results which show that the magnetic field is strong, and it's very directional in the two filaments, which can actually support against the collapse in the orthogonal direction of the spines, which are the direction of the filaments, basically. With that, I'd like to conclude my talk. So just to recap, I used the ammonia observations using GBT and VLA. Using a Bayesian analysis, I attempted multiple fits towards each pixel of the region, and I was able to get up to 3 components towards the pixels inside the filaments. By isolating the different components, I was able to see I was able to detect the single component results that was presented before, but additionally, I detected 4 components which show different structures. 2 of the components seem to be tracing the 2 infalling envelope, 2 sides of an infalling envelope of the filaments, and another component seemed to be tracing some infall of material towards the core itself. And this result of infalling of material towards already formed core challenges our idea that the cores evolve in isolation with a fixed mass. And if new material is being accreted by the core during its evolution, this indicate that we need to change our current understanding of the core evolution model. With that, I'd like to thank you for your attention, and I can take questions.
Thanks very much. Before I open up to questions, let me remind everyone that to submit your questions using the Q&A box at the bottom of the screen. I see one hand up, and I'm not exactly sure how to respond to that in this new version of Zoom. So we'll do the questions. But let me ask one point of clarification. And that is, you see a fairly ubiquitous broad component. Is that component still nonetheless subsonic?
In this case, this component shows both the cloud and the core in the same component, basically. So this is the extended component, which is ubiquitous, but inside the core, it seems to be subsonic throughout. And just outside the core, which is shown in this dotted boundary, we see the component being supersonic in turbulence.
Okay, thank you. There's also one clarification. The proposal deadline for GBT proposals and all of NRAO proposals is actually Wednesday, July 31st. So just please remember that. Cylinders, can the approximate volume of the filaments be determined?
Well, for this purpose, I'm using a very easy geometry. It's not a complicated one, but there might be some complicated structures of the filaments which make it difficult for us to get like the exact volume. But our goal in this is just to get like a upper limit of the material that's falling into the filament or the core. So we are just trying to see the boundary or the extent of the infalling material.
Mhm.
This is the upper limit. This is not a strict measurement of the infall rate.
Mhm. And can you remind us of how you got the core lifetime of 1,000,000 years?
That's from previous results. It's from the core models and simulations, not from my observations.
Okay. Here's another question. Is the infall along filaments?
Sorry?
Is the infall along the filaments?
We do see some velocity gradient that is periodic, but again, there is no strong gradient in velocity inside the filament that we see from our observations. So this is one of the, for example, in this velocity field, there is a slight velocity gradient from north to south in both of these two filaments, but they are not strong enough to suggest any infall in this case. What we do observe is the infall in the line of sight. We do not also observe any infall in the orthogonal direction. Along the filaments, there could be very small infall, but those could be towards these condensations, which I didn't go into details, but these are some dense structures inside the filaments, which are hypothesized to form individual stars at a later point of time. But there could be some material fall going into those condensations, but we do not really see any strong indication of like a large scale infall throughout.
Okay. We have time for one or two other questions if we have any coming in. We have no open questions at this moment. Oh, yes, here we go. Could the magnetic field originate from the detected young stellar object?
Well, no, but because we actually, okay, I'll show some very preliminary results from our magnetic field observations. These are some of the magnetic field vectors that we see here. These are the two filaments. The beam is quite large with JCMT. But what we observe is the magnetic field being very elongated along the filament. And the protostar that we observe is located somewhere here, which is very far and in a very small location. So I don't think it will affect the large scale magnetic field a lot. In the very localized region, it might affect the magnetic field, but I do not expect it to affect the magnetic field in the filament, which are quite large compared to the protostar.
Well, thank you very much. We have no more open questions, and that's good because we're almost out of time. I want to thank you very much for your presentation today. Let me remind everyone that it has been recorded and will be available for viewing on the Green Bank Observatory website in a day or so. Please join us in 2 weeks on July 31st for a presentation by Carmen Choza from the SETI Institute, New Targets and Enhanced Methods for SETI with Breakthrough Listen on the GBT. We hope you can join us then. Thank you and goodbye.